Welcome, everyone. Let's get started. So, course announcement. Problem 3, just a clarification that you can assume that you know the max flow already. This is not an algorithm for finding a new max flow that you don't know. This is, suppose that you were told what the max flow is, show that you could end up just taking order of number of edges steps in order to do the algorithm that we saw, the Ford-Fulkerson algorithm, if you knew exactly what augmenting paths to take. So again, the idea is if you knew what the right augmenting paths were, then you could find the max flow maybe more quickly than you could in reality. But there is actually a sequence of augmenting paths which may be hard to find, which would take you there. Are there questions about that or anything else? This is a baby otter. Any questions about the course? As usual, if you have very specific questions about the problems, please send them to me in the Slack. And also feel free to just ask to discuss problems if you feel stuck. I encourage everyone to discuss problems among themselves, but also feel free to discuss them with me on Slack or in office hours if you're just feeling stuck on a problem. Okay, let's get started. So I realized that I never really actually said what an array is from a sort of data structure perspective. And I think this is going to be useful in thinking about the data structures that we're looking at today, namely hash tables. So an array is a way of storing information in memory, like a lot of these other things that we've looked at. And in particular, creating an array with a certain length is like specifying a block of n spots, which are usually consecutive, in memory where things can be stored. And importantly, an array has random access, which means you can easily look at the kth spot out of n for any k. You can really fast work out what the k, if these blocks of memory, if the block of memory is typically consecutive, you just work out what the right place to look at is because you go k from the start. You can insert at the end of an array pretty easily if you have some extra space there until you exceed the allocated space, at which point you have to, I guess, find more space or kill that array and put it somewhere else, which can be a pain. And in particular, it's really a pain to insert something at the beginning or in the middle of an array because you have to shift everything afterwards further along. Because the blocks of memory are consecutive. So if you have stuff in a nice array here and you want to put something in the middle, you have to shift everything. The time complexity can be O of n, the number of things that you have there, because you have to shift a lot of things. And similarly, deletion is a pain. So again, the array gives you nice fast random access, but insertion and deletion can be a pain. Now, linked lists sort of do the trade-off differently. Instead, insertion and deletion are easier, but you don't have random access anymore. Each element is going to include a pointer to the next element of the linked list, and the memory might not be consecutive. But when you're at one point in the list, you'll know how to get to the next point in the list, but you won't necessarily know how to jump. You couldn't necessarily jump to the 10th element. The way you would do it is you go to the first element, then you'd say, okay, where's the second element? Where's the third element? And each time you would find a pointer to the next element of the list. You'd have to go on down the list. And in a doubly linked list, you also have a pointer to the previous element. So this is a doubly linked list where here you have something stored, you have 9, and then you have a pointer to the next thing where it stores 16, and you have a pointer to the next thing, which is where it stores 4. And so from 9, you can easily get to 16. From 16, you can easily get to 4 and to 9. But you couldn't immediately work out how to get to the thing 2 away. You'd have to go to 4 and then to 1. It's possible to get from any element to the next element and the previous one. That's called sequential access, but not to jump immediately to any element. So you don't have random access, you have sequential access. But, oh, sorry, and yeah, so getting to the mth element could take O of m time, because you have to take all these m steps. But insertion and deletion just take constant time, because you can insert at any point. So here, for example, I can insert at the beginning. And instead of having to shift everything over, I just insert this somewhere and change the pointer to 9 and change the pointer from 9 back to the previous element, and then done. Typically, there's a single sort of head element which just says this is the start of the list, and it points to the first element of the list. So you put this anywhere, you change where this points to reflect the 25. You change where this points to reflect the fact that it's no longer the first element of the list. It doesn't have to point to the head, it points to 25 now. Similarly, deletion. If you want to take something out, like take out this 4, it's very fast. Instead of having to shift anything over, you just look at the previous element, which was 16, and you say, okay, instead of pointing to 4, it's now going to point to where 1 is. 1 and 16 stay in the same place. You don't have to move anything. You just have to change the pointers. So again, linked list is a different trade-off between fast insertion and deletion and random access. You no longer get random access as you did in an array, but you get much faster insertion and deletion arbitrarily. Are there any questions? Okay. So sometimes we will want to store information associated to a given key. For example, the key might be a person's username, and the information might be their records. So one way to do this is direct addressing, where you can use the key as literally the pointer to the records. So maybe the keys are just some numbers, and you can say, okay, in the key 8 just points to the 8th block of memory. The key 1,000,002 points to the 1,000,002th block of memory. And you can number all the possible usernames, and that will give you blocks of memory. This will be called direct addressing, where you literally use the key as the exact pointer to the records. What's a potential problem with this? There are no potential overlaps because, or at least assuming that all the usernames are different. Yeah, you could have 2 people with the same username, but let's assume that you don't have 2 people with the same username. You set up your database so that you set up your system so that 2 people are always going to have different keys. So there is no hashing in direct addressing. You're going ahead to the next slide. There's no hashing yet, no hash function. This is motivation for why you want a hash function. Yeah, so it's really inefficient. There's a lot of unused space. But if you're literally allocating memory for every possible username, there are a lot of possible usernames. You need a huge amount of memory, and most of those slots are going to be unused. You can see here that, for example, 0 and 1 are unused, but if the keys are like picking usernames out of a hat of a trillion possible usernames, then you have to have a trillion blocks of memory here. Super inefficient. So as various people in the chat, we're already anticipating, you have the ability to fix this to some extent using hash functions. RAM is so cheap these days, though. There are a lot of possible usernames. You know, if you are interested in doing a little estimation, you know, typically a username is going to be up to, you know, it could certainly be 12 characters. I encourage you to calculate the number of alphanumeric strings of size 12, something like 36 to the 12 is going to be really, really large, and it's not doable even with cheap RAM. So I wouldn't suggest doing direct addressing for keeping a table of username data. Fortunately, there are hash functions. Yeah, thank you for calculating the number. It's very large. Yeah. Okay. And that would be the number of places in memory. You would presumably have to have actually several bytes associated to whatever, you know, depending on what it is the records are. Okay. So anyway, hashing is a way to deal with this particular problem. In hashing, there's a function h that takes possible keys, for example, usernames, as input. And the output is the address for the info which is stored for that key. So it's basically a way to say, okay, well, there are a lot of possible keys, but typically the number of possibilities for the output of the hash function is much smaller than the number of possible keys. It's sort of like, you can think of it as compressing K in some sense. Though the object of compression is typically different, but here we're trying to get a smaller number of possibilities for K. This is called a hash table. So here you have possible keys, and then here they get mapped to actual addresses in memory. And as you can sort of maybe guess from this, what is a potential problem with this? So we had a previous problem of just having to take vastly too much memory. Now what's the potential problem with hashing? It's naive form. Yeah. There could be two different keys which give the same hash function. You could have the hash function cause them to collide. And you know, since there are more keys than values of the hash function, this really could happen. So what gets stored there? This is called a collision. Okay, so how can we deal with collisions? There are different ways to do it, and I'm not going to go into different ways of handling collisions. If you're curious, you can look up things like cuckoo hashing, which involves like a complicated procedure of like moving things between several possible places if you end up with a conflict. But here we're going to do something. We're going to do something simpler, which is just storing a linked list at each spot. And so the first thing that you insert there initializes the list, and you have just one element in your list. And then each time you have something new, you insert it typically at the start of the list. So you sort of push everything back, though since it's a linked list, there is no real cost for doing that. It's very easy to just insert something at the start and say, okay, well, this is now the start of my list, and it moves to the thing key 1 is now the second element of my list. And then if I added key K3, then it would be K3, then K2, then K1. Okay. And this is called chaining within the hash table. So here you can see that, for example, we first inserted K4 here, and then we later inserted K1. And so K1 is now first. Here we inserted K7, and then we inserted K2, and then we inserted K5, and so on. And hopefully none of these lists gets very long, since finding something within a linked list is slow, because we have to just check through a lot of things. So if they were all in one linked list and we were trying to find a record, we'd have to go through potentially the entire linked list before we found it. Okay. Or I guess, are there any questions about this so far? Okay, let's analyze this a bit. So let's work with the assumption of simple uniform hashing for the moment. That is, the keys are drawn from a distribution that makes them equally likely to go in any slot, independent of the other keys. And in particular, we would have equal probabilities of, so like equal probabilities of having any value of the hash function. So for storing n keys with m slots, what is the expected number of keys stored in a single slot? Yeah, the expected number in each of the m slots is n over m. And that's just because the expected, the chance that any one is in slot number 1 is 1 over m. And so the expected number is just by linearity of expectation, summing 1 over m for all of the n things that you're inserting. Okay. So we can call this the load factor. You can write alpha as n over m. Depending on whether n is large or larger than m or smaller than m, we may have alpha greater than or less than 1. If we're given a new key, what is the expected time it takes to search to see if k is in the hash table? I guess I shouldn't say new key. If we're given a key, we don't know whether it's in the hash table. What is the expected time it takes to search to see if we are in the hash table? Any thoughts? I'm seeing some disagreement, and basically everybody's right, just in different cases. What do I mean by if k is in the hash table? If k is one of the things which are stored, if there's a record for k in the hash table. Okay, so we're going to have to go through one of the slots to see if it is there. Let's break it into two cases, depending on whether it's in the table already or not. Though it turns out we're going to get the same answer, regardless of whether it's in the table or not. So let's suppose that we have a key that is new and not already in the hash table. We still have to look for it. So there are two things here. Basically, we find the slot where it might be, but then if there's anything already there, we're going to have to search through that list to see whether K is actually one of the things there. And searching through that list might take a while. It depends on how long the list is. Okay. So we'll have to take theta of 1 time, so just constant time, to compute the hash function and then access the slot. And so for example, if there's nothing in the slot, then we're done. It's theta 1 time. But sometimes the slots will have stuff in them, and we'll have to check to see whether we are actually in the slot. And it's equally likely that K is hashed to any one of the M slots. Remember, that's the simple uniform hashing assumption. Very hard to say. So the expected time is going to be just theta of 1, and this is the constant that it takes to compute the hash function and then access the slot, just some constant time, plus so there's a 1 in M chance that it's in slot 1, a 1 in M chance that it's in slot 2, and so on. So it's sum over all the possible slots, 1 over M times expected time searching if we had to search that one slot. How can we simplify this? What is the expected time to search one of these slots? When you're thinking about it, we're going to have to we're going to have to search a slot that has some stuff in it. And we know, remember, this is a key that's not actually in the hash table. So we're going to have to go through the entire list in that slot. And then when we get to the end, we're going to say, oh, no, it's not there. So the time required to search the slot is just the length of the list in that slot. So it's the expected length of the list in the slot, which is, sorry, I guess I should have said theta of, this should be theta of alpha. So remember, the length of a slot is just alpha, the load factor, n over m. And again, sorry, this is a theta, not a big O. I apologize for that. So this is, what does this whole thing become? Theta of 1 plus the sum from I equals 1 to m of 1 over m times theta of alpha. What is this? Well, it depends. So we have theta of 1 plus theta of alpha. And this could be, so if alpha is less than 1, then this is just theta of 1. But maybe, like, depends on, I didn't really say what is changing, whether it's m or n. And just to be safe, we can write theta of 1 plus alpha. So for example, then this will tell us that if n is increasing and m is fixed, then this just becomes theta of n. But if, on the other hand, n and m are both very large, but like they're equal, then this is just theta of 1, constant time. Questions? So if you've hashed k, can't you just check if something is already at address that address? So yes, but if something is at that address, you have to go through all the things already at that address. Agreed. If there isn't anything, that's really fast. We're never having to search the whole hash table. We're only having to search the slot where there are collisions. But we're just basically assuming there are some number of collisions. There might be none, but there might be a lot. There's a question. Hash tables are not O of 1. I feel like I've been lied to. It depends on how you implement a hash table. This is a really simple way to implement a hash table. We'll see a slightly better way to implement hash tables. But I mean, if you have if you have a reasonable load factor, then it's fine. But you do have to deal with the situation of having multiple things that hash to the same thing. Like you can't, there's no free lunch here. You can't store a ton of things in like almost no space and not have to, or almost no slots. You know, if you just had 2 slots, hashing to 2 slots is not going to give you very much savings. Basically, what hash tables are, you know, they're designed to make the best use possible of the space that you have. But if the load factor is really high, there's a limit to how good you can do. If you're sort of storing multiple things at the same address, isn't it better to expand the dictionary? Not necessarily. So it's not necessarily better, because if you're only having a very small linked list there, then it's probably better to, like, if there's a small chance of having a couple of collisions, you can deal with those. Basically, what this is saying is if you have a very small number of collisions, then this is how you resolve them. You would never want to do this if you're expecting to have a huge number of collisions, because searching through linked lists is really time intensive. And this is basically what it's saying. If you have a very high load factor, you never want to do this. But if you have a relatively small load factor, then it's totally fine. Does that make sense? Okay. So now we only did one situation. What if we're given a key that's already in the hash table? How long will it take to find that? And you know, I first looked at this and I was like, oh well, clearly it's the same time if it's a new key versus an old key. But no, it's not quite the same. Let's assume it's equally likely to be any one of the keys in the table. What's the expected time to find its records? Well, the analysis is a bit different, because now you're actually more likely to look in a longer list. Why are you more likely to look in a longer list than a shorter list? Well, because a longer list has more things in it. And you look in the list which has your key in it. This is sort of like my friends are likely to be more social than I am. If you have a friend, like somebody who has a lot of friends is more likely to be your friend, as it were, because they have a lot of friends. A longer list is more likely to be where you search because it's a longer list. It has more things in it. So instead of taking a random list from all of your slots, you're biased now towards the slots that have more things in them. So the analysis is a bit different. You could end up with a different answer. Let's take a look. So suppose that the hash table was created by inserting some keys in this particular order. K might be any one of these with equal probability. Let xij be the indicator variable that we have a collision with I and j. So in particular, xij is 1 if we have a collision and it's 0 otherwise. What is the expected value of the position of ki within its slot? So ki is in some linked list. There's a linked list at the slot for ki. Ki is in some position. We're going to have to basically find it by going out to that position. So like it might be 10th in the linked list, and then we'd have to go 10 steps along the linked list in order to find it. What's the expected value of the position within the list? Yes, it is the length of the list over 2, but that is one way to express it, absolutely. I'm going to express it slightly differently. because I want to express it in terms of x, ij. So the expected position is 1. There are different ways to do this, by the way. So if you're thinking about doing this a different way, I am not telling you that that is the wrong way to do it. It will give you the same answer. It's just I'm doing it in a particular way. So the expected position is 1 plus the expected number of elements inserted after we inserted ki. Right? So if we inserted anything after ki in the same slot, then it will collide in the same slot. Then we will have pushed ki sort of 1 position further in the list. So, if there were no collisions after ki, with ki, if we never inserted anything in the same slot, then we'd have to check 1. The position will be 1. So that's what this 1 is. And then this is just the number of things after ki that collided with it. So the number of things that we inserted in the same slot. Questions? Again, this is the number of things that we expected to insert after ki. So ki plus 1 all the way up to kn, they might collide with ki. If they collide with ki, then they push ki 1 element further along its list. So this is just counting the number of things that we inserted after ki. That's why this sum starts at I plus 1. It goes up to n. The things we inserted after ki, which could collide with ki. If they collide with ki, then they increase this thing by 1. Question: when we insert to the linked list, are we adding to the head of the list? Yes. That is important. We are adding to the head of the list. The analysis would be very, very similar if we added to the end of the list, but each time we insert to a linked list, we push everything that's in the list 1 further. We just insert at the start of the list. And the reason why we would do that is so that we don't have to go all the way to the end of the list, right? To traverse a linked list, it's a bit expensive. And so we want to insert fast. And so we insert at the start of the list. OK. We could also maintain like an end of the list thing. So we could insert it at the end of the list. And that would be fine. But we'd have to sort of like make sure that we knew where the end of the list was. But yeah, we insert things after at the start of the list. OK, so now we know the expected position of ki in its slot is this. Now, since k could be any of the ki's with equal probability, remember we're trying to find one of the keys that we inserted. We don't know which one it is. The expected position of k in its slot is just averaging over this. It's the average over all possible ki of this thing. So let's just rearrange this a bit. First of all, we can pull out this 1. Summing over 1 and then dividing by n, that'll give us a 1 out in front. OK. And then we just have these 2 summations, which are just the same as before. OK. Next thing we can do is, what's the probability that I and j collide? Well, the probability that I and j collide, since we're under this simple uniform hashing assumption, is just 1 over m. There is a 1 over m chance that any 2 things will collide, because there are m possible slots. You've put each of ki and kj into a random slot. So what's the chance that kj's slot is the same as ki's slot? It's just 1 in m. OK. So then we have this. what can we do with this? Well, we can rearrange it a bit. We can say, okay, this is 1 plus, I mean, the m isn't, there's nothing in here that's changing the m, so pull out the m, 1 over n m. And then this inner summation is just n minus I. There are n minus I of these 1s, so okay, great, we have this. How can we calculate that? Let's just write it out. It's 1 plus 1 over nm. And then the summation is n minus 1, n minus 2, all the way down to 1. Or actually, all the way down to 0. So we know what the sum of the numbers 1 through n minus 1 is. There's a formula, and that'll give us this. This is just the same as, remember, when we're summing up the numbers 1 through n, we get n plus 1. We get n times n plus 1 over 2. And this is just the same thing if you had n minus 1 instead of n. So this is equal to 1 plus n minus 1 over 2m. So what's the time that it takes to search for k? The expected time. This is the expected position of k within the slot that it's in. Do we have, and previously we had that the time was theta of 1 plus alpha, where alpha is equal to n over m. What is the expected time now? In the situation that we have the key is actually in our hash table. Previously, we were looking at the situation where it's not in the hash table. Now we're looking at the situation where it is in the hash table. It's not exactly the same as this expected position, but it's basically the same as this expected position. We multiply by a constant because it takes us a constant amount of time to check each position in the linked list. And then there's also the amount of time that it takes to do the hash, like compute h of k, which is again theta of 1. So this is just theta of 1 plus alpha. The 2 in the denominator doesn't matter because theta is including constants. And so the overall time is just theta of 1 plus alpha, which is again theta of 1 plus alpha. Or again, the reason why we have 1 plus alpha is because sometimes alpha is less than 1 and sometimes alpha is greater than 1. And this is just basically saying if alpha is greater than 1, it's theta of alpha. If alpha is less than 1, it's theta of 1. Why are we including the constant term if it's just 1? The reason is because n might be a lot smaller than m, in which case this thing would be really small, and 1 would be the dominant thing. We're trying to basically include two cases. One where you have many more things you're trying to hash than slots, where n is much bigger than m, and also the situation where m is much bigger than n. So you have, many more things. If m is bigger than n, then you have more slots than things you need to put in them, and then you're great. But you could also have n much bigger than m, where you have more things than slots. And then this is sort of telling you that it's theta of alpha, which is the load factor. Questions, more questions. In this analysis, for the case that key k is in the hash table, where does the intuition that k is biased towards longer lists come up? It's not really being incorporated into our analysis. Another way to get it is to say that basically what you're doing is you're going to be taking our previous analysis, and you're going to be sort of multiplying. You're going to be looking instead of at the sort of the expected like length of a list, you're going to be looking at like length of a list squared, sort of. And if you calculate that out, you'll end up finding that it gives you the same thing. That's another way to do this. Okay. Any more questions? So to calculate big O, we assumed that our hash function was optimal. I don't know that it's, there isn't, the assumption we used was simple uniform hashing. So it's not assuming that the hash function is optimal exactly. An optimal hash function would make sure that would like adapt to whatever the keys were and would have as few collisions as possible. We are not having as few collisions as possible. We're just having completely random collisions. It's simple uniform hashing. So it's easier to analyze, but it's not the best it could be. The best it could be would be literally reducing the number of collisions. We're just making them random. But now let's take a look at that assumption in a little bit more detail. But first, let's see a couple of different ways to do the hashing. So if we know that the keys k are real numbers with the uniform distribution, say on the interval 0, 1, though other intervals would be similar, we could just do the hash function of the floor function of km, where floor function is just, it's just rounding down to the nearest integer. So this is just basically saying multiply by m and then round down. So that will give you something that is either 0, 1, or m all the way up to m minus 1. And it gives equal probability. It's basically breaking your interval into m equal pieces. And if you know that the keys are randomly along this interval, then you're great. The floor notation, is this a floor notation? Broken brackets. So in LaTeX, you would write this as \L floor and \R floor. There's also rounding up, which is with a ceiling function. Anyway. And that would work too here. So if k are integers, then we could use residues modulo m, for example. We could say that you're just taking the residue modulo m, or I'm going to use equals k modulo m to indicate that it's equaling the residue modulo m. So it's 1 of 0 through m minus 1. Though, again, we need to know that keys are equally likely to have different residues, which is a big assumption. That might not necessarily be the case. If we, in practice, I mean, one could do this. It's not an unreasonable thing to do if you think that your keys are going to be pretty randomly distributed. Typically, we would want to avoid certain m in this case, in particular powers of 2, because often if you take a residue modulo power of 2, like if you're working with sort of computer data, often powers of 2 are special, and like taking a residue modulo power of 2 is just like looking at the last bits. And that's a little bit tricky. Like you will often find patterns there that are bad, and you don't want patterns for a hash function. You want this to be as random as possible. So a prime number is often going to give you sort of the most random thing if you're taking residues modulo m. And that'll give you the fewest collisions. And we're going to sort of look at a situation why, some intuition for why this is the case. Questions? So we have a problem with all the things that we did before. If an adversary gets to pick the keys for either of those hash functions, they can make all of the keys collide very easily, which is not a good thing. So the idea of universal hashing is that the hash function itself is picked randomly, to avoid this. So specifically, the goal is that for any pair of keys, even if they're not random, we are likely to pick a hash function where they don't collide. And it's basically, it's like you can think of, I mean, previously with simple uniform hashing, we were like, well, assume the keys are random. We're gonna do okay. Now we're gonna say, I don't care about the keys being random. The hash function is random. And so moving the randomness to the hash function means that we can control it, because we don't necessarily control the keys, but we definitely do control the hash function. So formally, the way that this works is let H be a set of possible hash functions. We're going to pick some function at random uniformly from this set. So the definition of a universal set of hash functions is that for any different keys, k1 and k2, the probability of picking a hash function where these two collide is at most 1 over m. So remember, that was what we wanted for simple uniform hashing, is having 1 over m being the probability that they collide. That was just the case in simple uniform hashing. But now we'd like that to be the case. But again, the randomness is not about the keys. The keys, they could be designed by your adversary. They could be designed to be really bad. But because you're picking a random hash function, there's a low likelihood that they're going to collide, just because most of the hash functions will cause them not to collide. Questions? Okay. So let's look at one way to design a universal set of hash functions. Let's assume that the keys are integers in some specified range. Let's pick a prime that's bigger than that range, so that every possible key is between 0 and p minus 1. So since we have more keys than slots, or if we're probably working in the regime where we have more keys than slots. We have p being greater than m. Now, the way we're going to define our set of hash functions is we're going to say for every a that is between 1 and p minus 1, so it's all the residues modulo p except for 0, and b, any residue modulo p, anything from 0 to p minus 1, we're going to define the hash function hab of k is equal to ak plus b modulo p. So we're taking the residue mod p. This is one of the things. Taking the residue mod p means it's 0 through p minus 1. And then we're taking another residue. We first take the residue modulo p, and then we take the residue modulo m. And m is smaller than p, so it sort of makes sense to do that. So we might first take the residue modulo 17, and then we might take the residue modulo 3 after that. And that gives us something that is between 0 and m minus 1. So there are m possibilities for it. So it goes into one of our m slots. This is a hash function. And it's a hash function that depends upon a and b, which we can pick randomly from these two sets. How many choices of the hash function are there? So we're picking A and we're picking B, and A has P minus 1 choices and B has P choices. So we're going to get P times P minus 1 choices for the hash function. So we will prove that this set of hash functions is universal. But I think we're running out of time now. So let's finish this proof next time on Monday. And I will stick around for any questions.